Yeah, all right. Our next speaker is Abi, who will be talking about beyond complexity scores, algorithmic information dynamics. Yeah.
Yes. Oh, thank you. Good afternoon, everyone. Thank you for granting me this opportunity. This talk presents findings from our ongoing work linking algorithmic information dynamics and complex systems. This work was co-produced and supervised by Dr. Hector Zeno. So in this work, we benchmarked various complexity estimators across complex systems. We show that algorithmic information dynamics, or AID for short, as developed by Senel et al., provides a perturbation-based map or generative structure that can support in silico causal inference in complex dynamical systems. We propose that AID or AID sits at the intersection of this symposium's communities of thought. It inherits minimal description length principles from AIT, uses methods such as compression and block decomposition method that my colleagues and collaborators have just shown to estimate Kolmogorov complexity, and it applies perturbations as interventions to decode potentially and potentially control system dynamics. So there are many scalar metrics in the family of so-called complexity estimators and measures. Most remain useful and complementary, but are dependent on the same arguments that were just put forward. They rely on statistical distributions, or they usually identify statistical regularities as patterns, or quantify only certain characteristics of otherwise collective and emergent behaviors in complex dynamical systems, such as redundancy, synergy, or uncertainty, or even multivariate information. And these are only information features of complex systems that do not necessarily imply causality or identify causally informative signatures of a dynamical system's evolution, its trajectories. And AID, through BDM perturbation signatures, provides a powerful framework for mechanistic causal discovery. So this slide is very familiar territory to all of you. So not a lot of attention needs to be put right now. But in brief, algorithmic information dynamics begins with the uncomputable, or more appropriately, the semi-computable Kolmogorov complexity, K of X for some object X, such as a binary string, a matrix, image, graph network, and through algorithmic probability, M of X, and the coding theorem, CTM, the block decomposition method provides a practical estimator for Kolmogorov complexity. And I don't want to go into the details of that. We already know that K of X measures the length of the shortest program capable of generating X, and CTM estimates the complexity from the distributions of many programs, and BDM combines them across blocks. So the important point for the rest of the talk is that BDM estimates description length in a way that is closer to the generative structure than other measures like Shannon entropy, or the list of complexity estimators that we benchmarked complex systems. And this is, as was demonstrated by Professor Zeno et al. In 2019 in iScience paper, Algorithmic Calculus. AID turns estimated algorithmic complexity into an intervention map or a perturbation landscape for mechanistic discovery and even reprogrammability from the vantage point of controllable or control systems and dynamical systems towards some desired goal-directed behavior. And teleonomy is one of the feature hallmarks of intelligence. So the statistics panel on the right, that's boxed, it's summarizing the main robustness results that we obtained from this experiment. So we categorized across 11 different complex systems that I'll show you on the next slides, from 9 binarization thresholds ranging from 0.1 to 0.9, and we investigated various complexity measures. And here's the first slide of a list of comparison of some measures that we benchmarked. In brief, Shannon entropy and lossless compression algorithms like, LZW, gzip, deflate, doesn't matter what. They are quantifying uncertainty and redundancy respectively. We also looked at epsilon machine statistics like CMU, which are quantifying the minimum predictive state memory required to optimally forecast some dynamical system or process. And this was demonstrated initially by Crutchfield et al. And CMU is the Shannon entropy of this inferred causal state distribution, whereas H of mu is the remaining entropy rate, so the entropy generated per time step. And we also looked at Carl Friston's variational free energy principle using a hidden Markov model network, which is basically representing the states, the unobserved states linked by transition probabilities. And this is commonly used in fields like active inference research and may be pertinent to agentic AI. But unlike algorithmic information dynamics, I'd like to stress again that it does not perturb individual components or elements to produce a directional assigned causal information signatures and perturbation landscape. So they are very useful and bound by statistical distributions or for detecting statistical regularities, but not beyond that. And this is the remaining list of other measures that we compared across. So partial information decomposition, many of you might know it's kind of like an extension of mutual information. And the more popular, recently popular PHI or IID from Integrated Information Dynamics. It's even proposed as a mathematical framework for consciousness. And we also looked at other measures, but in general, they're all investigating into synergistic, redundant, and unique information factors, more like a multi-information theoretic. And there are Python packages for all of them. And we also looked at ROSAS-SI, which is part of the ROSAS and Mediano information theoretic framework, where they propose that some other measures can detect causal emergence, and it tests whether a present macro variable predicts the future beyond the summed predictions of its microvariables. O information is similarly another measure that's related to total correlation. And also very recently there was epiplexity, and epiplexity, as we will show, is a more bounded minimum description length objective. It's more resource bounded and performs suboptimally to block decomposition method. So it can be written as a functional of the algorithmic information dynamic perturbation landscape. So the overall framework, the central method workflow is that we had 4 stages. First, we construct the 11 different complex systems we tested, including cellular automata of various rules, 2 strange attractors, the Lorenz and Rossler attractor, some fractal patterns like Mandelbrot and Julia sets, and various graph networks ranging from random networks, Erdos-Renyi, Barabasi-Albert, Watt-Strogatz, all the way up to biologically driven actual empirical E. coli and yeast gene regulatory networks. And then we represent them as arrays, graphs, or trajectories, and then perturb multiple elements and across the binarization thresholds. And we measure the complexity measures that I just showed you on the previous slides. So our first result was that you can see all the complex systems on the x-axis, and the y-axis are just showing some log scale threshold averaged value of the different metrics, and the error bars are the 95% threshold resampling intervals, confidence intervals, and the blue bars are representing the global static 2-dimensional block decomposition method. Larger values are indicating that a longer estimated description length for the whole system, and you can see that it's followed by in orange and green, the block and cell level block decomposition method. And this is just telling you that high static block decomposition method alone may also reflect randomness, but this is circumvented by block and cell level block decomposition method, which can reveal some kind of organized complexity or structure within these heterogeneous systems. And this is perhaps the most relevant result. So this is a sensitivity and stability plot, and I focused only on the block decomposition method here. On the next slide, I'm showing the other measures, but the axes are of central interest here, and it's basically comparing the threshold responsiveness on the x-axis. Of the fraction of the 11 complex systems that I showed you, in which one of these measures um, is changed across the binarization threshold. So on the y-axis, you have the ranking stability using Spearman agreement, and the bars that you're seeing are the bootstrap 95% confidence intervals. And we can see here that algorithmic information dynamics measures, so block decomposition method, they responded in 100% of the investigated systems, with obviously with some uncertainty across the 11 systems. And they also showed the highest concordant metrics, namely the Spearman correlation was roughly 0.88 or 0.89. Likewise, for the intraclass correlation coefficient was also 0.9, and also Kendall's W. So Kendall's concordance was also high. So these measures had the highest for these stability response curves across all other complexity estimators that we benchmarked across these 11 complex systems. And you can see here that the rest of them are just centering around like 0.35 for responsiveness, and they have varying degrees from 0.6 to 1 for their Spearman agreement. And due to the lack of time, I'll just quickly rush through this. I had tokenized my time more generously. So here, you can see that we also repeated this on fractal perturbation landscapes. To the left, you can see the Mandelbrot and Julia, and we looked at their BDM signatures, and we compared it to other measures like epiplexity is shown there. And what we saw in general was that uh, while block decomposition method was very sensitive to these perturbation signatures, like you can see those blue lines, it's picking up the spectra. Epiplexity is enveloping into some kind of a global metric that summarizes only the bounded coded frontier. It acts more like a compression algorithm. It's a resource bounded compression like minimal description length, and only summarizing the full algorithmic structure and perturbation signatures that we can obtain using block decomposition method. And the networks on the right are just showing various graph networks. Like I mentioned, we tried various random networks and biologically driven networks and compare them. And due to time limits, I will not go through. And this is just repeating the same result on a cellular automata, rule 110. And you can see here in purple, the bars, it's showing the beautiful distribution of BDM signatures. And we don't get that same level of sensitivity or prediction from other measures. And this might be pertinent to the machine learning community, but when you use machine learning like recurrent neural networks, or more specifically echo-state networks and reservoir computing, for predicting where the trajectory of a chaotic or complex dynamical system will go, we can, by combining it with the various so-called complexity estimators or measures, we can see that AID and specifically block decomposition method-based perturbation identifies which states or perturbation changes its outcomes, and collectively they can accurately forecast the dynamical system with mechanistic interpretation and allow state space attractor reconstruction, as was demonstrated by this morning's talk by Dr. Zeno. And this also allows controllability and system reprogrammability. And I will not go through some of these results, but this is all to say, to conclude, the main implication from this study, these benchmarking results across this pool of complex systems, is that a complexity measure or estimator or some model, a complexity model, when combined with machine learning, for instance, can be accurate and they can provide us some complementary insights. However, it is still unsafe or uninterpretable in many cases if we do not know which algorithmic perturbations destabilize it. And we can conclude here that AID signatures could be used to regularize, for instance, latent spaces, identify fragile states in the controllability of dynamical systems. And most of these currently existing so-called complexity metrics are only detecting statistical features of emergent behaviors in complex systems, often in the form of uncertainty, synergy, or redundancy. So thank you very much. And thank you to Professor Zeno for being my mentor and supervising me, and to everyone here for your immense contributions to the field. Thank you.